Hi boys and girls, this is your math e-learning lesson for Friday, April 24th. We're going to be taking a look at lessons 124 and 125. So let's begin with 124, estimating area. So before we talk about estimating area, let's just take a look at this orange square up here. So if we wanted to figure out the area of this square, we would look at the number of square units that covers the surface of this figure. And so in this case, you would see you have 1, 2, 3, 4. There are 4 squares that covers the surface of this larger figure, of this larger square. So we would say that the area of this large square is 4 square units. Now, if you know the unit of measurement that's used, if for example I told you that these are 1-inch squares, then we could say, well then the area of this figure is 4 square inches. When you don't know what the unit of measurement is, then you simply just call it units. But if you know it's inches, then you can say inches. In this case, 4 square inches is the area of this figure. Now, what happens when we start to look at a figure like this triangle here, where when you look inside, yes, you do see some whole squares, but you also notice that there are half squares in here. So this is where estimating area comes into play. So let's take a look. There are 2 different ways that you can figure out the estimated area. And they're similar, but they are slightly different. So let's take a look. So the first way to figure out area of something like this, where you don't have all whole squares, is to start by counting up the whole squares that you do have. So we look for all of our whole squares, and so we say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 whole squares. I'm just going to write 12 right over here. Remind myself that there are 12 whole squares. And this first strategy for estimating area says that then you look at all of the pieces, all of the parts of squares that you have, and you look to see if you can put pieces together that will make up a whole square. So when we look here, it's clear that this piece and this piece are each a half of a square. So this half plus this half gives me another whole. I'm just going to put a little tally mark for that one. And then this half plus this half gives me another whole square. Over here I have this half plus this half. That makes up another square. And then this half plus this half makes up one more whole square. So now the area for this triangle, we can say, well, we had 12 whole squares and we were able to make 4 other whole squares. And obviously 12 plus 4 equals 16. So we can say the area is 16 square, and we will use inches since I've already told you that they are inches. Okay, so that's 16 square inches. Okay, now what I told you, there are 2 ways that you can do your estimating. Now, the second way for this one, well, we're going to do it, and you're going to see how the answers vary with these 2 different methods. So I'm just going to erase the X's for a minute. Okay, now, once again, you always, in both methods for figuring out the estimated area, in both methods, you always start by counting up the number of whole squares that you have. So that we've already done, we know that we have 12. Okay, now in the second method, we don't look to put parts together. We don't look to piece them together to make whole squares. The second method says anytime you have a half of a square or more than half of a square, you count it as a whole square. In this case, if you were to do that, then you would have to say that you have 1, 2, 3, 4, 5, 6, 7, 8. You'd have to say you have 8 more squares because each of these are a half, and it says anytime it's half or more than half, count it as a whole. So in this case, you would have gotten an estimated area of 20 square inches. Okay, because you had 20 whole ones, and then all of the half ones you also counted as whole ones. Okay, so the first estimation you came up with 16 square inches, and the second way of estimating for this particular figure gives us an estimation of 20 square inches. Now, personally, with this particular shape, I would have used the first method, and the reason for that is it's so clear to see that these are half squares, so it's so easy to say, okay, well, I know the two halves make a whole, and so by doing that, I know that I'm going to, it's probably going to be a more accurate answer, okay, because again, it's so clear that these are half squares. And with two halves equaling a whole, it makes it very easy to come up with a total of 4. And then the 12 plus 4 equals 16. Okay, this is also an acceptable answer, but in this case, with so many that are exactly half, again, because you have exactly half, it makes more sense to just put the two halves together, giving you one whole. Okay. Sometimes, though, you're going to have a variation of pieces, and you'll see how that works out. Okay, so let's take a look at another figure. Okay, here's another figure, this time not a perfect triangle, just an odd-shaped figure. And we need to figure out the area of this figure. Now again, remember we're just doing an estimated area. This is not exact, it's an estimated area. So let's take a look. Again, we're going to start out by counting up the number of whole squares that are in this figure. Okay, the number of whole squares in this figure. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there we have exactly 13 whole squares. Okay, 13. Then we can take a look. Now, when you look on these, you'll see that, okay, well, here we have 2 halves, but then here we have less than a half, and this one is more than a half, and this is less than a half, and this one's more than a half, and this one's more than a half, and this one's way less than a half. This one is almost a whole, and this one is less than a half, and this is about a half. So now you can see where we have different pieces of squares. And so it would become much more complicated to have to start piecing your halves, or piecing your squares together, because in this case we have a couple of halves, but then we have other pieces that are different sizes. So when you have a figure like this, it's best to go with the second strategy, which is count up your whole squares first, and then anything that is a half or greater, you count as another whole one. So in this case, we would say this is going to count as 1 because it's a half, and that will count as 1 because it's a half. This is way less than a half. This is much greater than a half, so that's another one. So we're up to 3. Way less than a half, greater than a half, so that's 4. Greater than a half, 5. Greater than a half, 6. Way less than a half, less than a half, and a little bit more than a half. So we now have 1, 2, 3, 4, 5, 6, 7. So in this case, then, we would be adding on 7 more, giving us an estimated area of 20 square inches. Okay, much easier than that first strategy where we would have to look to see how can we make whole squares. So in this case, we would just simply count up all of the whole squares that we see right away, and then anything that's a half or greater counts as 1. In other words, counts as a whole square. So this would give us an estimation of 20 square inches. Okay? And one more example. Okay, here we have a hand. And so this would be very difficult to try and figure out, okay, well, which pieces go together to create a whole square. So let's use again that second strategy, and we'll start by counting up whole squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I did count this one, which is just slightly under a whole one, and I did count it as a whole. So I counted up 11 that were whole ones. And now, and since I'm using the second strategy where I'm going to count anything that's greater than a half as a whole, it's fine that I counted that one as a whole. So we take a look. This is greater than a half, so that will count as a whole. This is more than a half. This one is more than a half. Here, if you look at this one, I'd say yes, that's more than a half as well. Again, it is an estimate, so use your best judgment. Greater than a half, greater than a half. Okay, this one, greater than a half, greater than a half, greater than a half, greater than a half, greater than a half. Okay, and again, it is an estimation, so you do need to just sort of use your best judgment. Some of them it's tough to say, you know, like this one, is it, isn't it? Okay, but I look and say, well, if I continue this, okay, this red that you see here, if I continue that straight up here, okay, this piece here is way less than a half. Okay, so that kind of makes up for this little difference that's over here. So I say yes, this is greater than a half. Again, use your best judgment. Okay, so we had 11 to start out with, and then we added on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually adding on another 11, giving us an estimation of 22 square inches. Okay, so again, two different ways, two strategies for estimating area. Both ways, you start out by counting up the number of whole squares that you see. And then you'd want to write it down, okay? Because when you start to count, you might lose track. So write it down. Then the first strategy is, if you can see that it's very easy to see that you have two halves that equal a whole, then by all means, you can put your two halves together and count it as one whole. When you have a figure like this, where you have some odd shaped pieces, it's going to get a little too complicated to try and figure out which pieces fit together to give you a whole. So the second strategy would be best, where again, you count up all of your whole squares first, and then anything that is greater than a half or greater, then you would count that as one whole as well. Okay, because then that makes up for the difference for, you know, those smaller pieces too. Okay, so that's estimating of area. Now, let's move on to the next lesson, 125. And lesson 125 is reducing fractions. Now, I know we had already started working on this in school. This had come up with a couple of, I believe, the problems of the day that we had been working on. So again, not totally new to you, okay? But let's take a look. So if you needed to reduce a fraction, okay, you're going to divide the fraction by name for 1. Now you need to remember that when you are reducing, let's say we had, let's say we're doing 4, 6, okay? All right, so if you were going to be reducing 4, 6, what you want to do is you are looking to write a fraction that uses smaller numbers. Okay, now ironically, when you're doing that, your fraction with the smaller numbers actually gives you the bigger pieces. Remember, that's the difference with fractions. In fractions, you know, what seems to be the larger numbers are actually the smaller pieces, because if you needed to divide something into 6 pieces and have to share it, you're going to get a much smaller piece than if you had to divide the same thing into only 3 pieces. With 3 pieces, you'd get a much bigger piece. But anyway, when you have a fraction and you're looking to reduce it, you're looking to get the numbers to be smaller than what you've started with. And the way that you do that is by dividing. And we say that what we do is we're dividing by a fraction named for 1. And the reason that we say we're dividing by a fraction named for 1, well, first of all, we are. Okay, but remember that a fraction named for 1 means that the numerator is the same as the denominator. And in order to reduce a fraction, whatever you do to the numerator, you must do the same thing to the denominator. So with 4/6, I want to reduce it by a fraction named for 1. Often you will use 2/2. Okay, 2/2 is a fraction named for 1, because if you eat 2/2 of your sandwich, it means you've eaten the whole sandwich, one whole sandwich. Okay, so we would divide 4 divided by 2 equals 2, and 6 divided by 2 equals 3. So we have reduced 4/6 down to 2/3. Now, if we look at 2/3, there's nothing that we can reduce 2/3 by. And the reason I know that is because there isn't a fraction named for 1 that I could use here. Because remember that you always have to, whatever you do to the numerator, you have to do to the denominator. So if I tried using 2/2 again, sure, I can do the numerator, 2 divided by 2 is 1, but I cannot say 3 divided by 2. The reason I can't do that is because if I do that division, 3 divided by 2, I end up with a remainder. And when you're reducing fractions, you're not going to divide by anything that's going to give you a remainder. Okay, let's say we had the fraction 6/8. Okay, and we want to reduce 6/8. So I need a fraction named for 1, but again, I need to be able to divide both the numerator and the denominator by the same number. So I can do 2, or at least I can look to see, and I know that I can divide 6 by 2. I know I can divide 8 by 2. So let's do that. 6 divided by 2 is 3, and 8 divided by 2 equals 4. So I can reduce 6/8 to 3/4. There's nothing further that I can reduce 3/4 to. Okay, because if I divide it by 3/3, I can divide the numerator by 3, but I can't divide 4 by 3. I could, but I'd have a remainder, and that doesn't work with reducing fractions. Okay. All right, how about 6/9? And you'll see that you can often use 2/2. That is a common fraction name for 1 that you use in reducing. So you could take a look, and at first glance you might think that you could use it here because you know you can do 6 divided by 2. However, you cannot do 9 divided by 2. That does not divide evenly. Okay, so you're not going to be able to use 2/2. So you need to think of something else you could use. Okay, so my next choice, and this is just a little helpful hint when you are trying to do the dividing to reduce your fractions. Often you'll use 2/2. Can't use 2/2, then I look to go to 3/3, or then I would go to 4/4. Okay, most times you're going to stick with some of those lower numbers. So I can't do 2/2 because I can't do 9 divided by 2 evenly. So what about 3/3? I can divide 6 by 3. Can I divide 9 by 3? Yes. So I'm going to do 3/3. 6 divided by 3 equals 2, and 9 divided by 3 equals 3. So 6/9 can be reduced to 2/3. Okay. Let's do 6/7. Okay. I want to reduce 6/7. All right, well, let's try 2/2. I could do 6 divided by 2. I can't do 7 divided by 2. All right, that doesn't work. What about 3/3? I can say 6 divided by 3. I can't do 7 divided by 3. 4/4, can't divide neither 6 nor 7 by 4, so that's not going to work. 5/5, no. 6/6, there's a 6. How about 6/6? No, because I can't divide the 7 by 6. All right, you could go through all of your fraction names for 1 in this case, and you're going to see that you cannot divide 6/7 by any fraction name for 1. So what does that mean? It means you leave 6/7 as it is. It means it is already reduced. It cannot be reduced any further. And you're going to find that that's going to happen, that there will end up being some fractions that are already reduced and you cannot reduce them any further. So then you would just leave it as 6/7. Okay, let me see. Let's do a few more. How about 6/7? We did 6/9. How about 8/10? And we want to divide, or we want to reduce 8/10, so we want to divide by a fraction name for 1. So what are we going to use? All right, well, let's do 2, because I know that 8 and 10 can each be divided by 2. So I do 2/2. And 8 divided by 2 equals 4. And 10 divided by 2 equals 5. Okay? And if I look at 4/5, that cannot be reduced any further. Okay, now sometimes, and I just wanted to show you this, let's say we were doing 8/16. And so you said, okay, I know both of those numbers can be divided by 2, so let's do 2/2. Okay. So 8 divided by 2 equals 4, and 16 divided by 2 equals 8. Well, now look what happens. When I look at 4/8, I notice, wait a minute, but I can still divide that further. And so I need to divide it even further. And so I would say, okay, what can I divide the 4 and the 8 by? And you might say, well, you can divide both of them by 4. So let's do 4/4. And then we have 4 divided by 4 equals 1, and 8 divided by 4 equals 2. So actually 8/16 should be reduced to 1/2. And remember what I told you, when your numerator is half of the denominator, it's always equal to 1/2. Okay, now how could we have eliminated all of these other steps? Well, if you looked at 8/16 and you realized, you know what, I can divide by 8/8. And 8 divided by 8 is 1, and 16 divided by 8 equals 2, and 8/16 equals 1/2. Okay, so when you are reducing your fractions, you want to look at what you have gotten as your answer, because sometimes that fraction can be reduced even further. Okay, so remember, the idea is to get the smallest numbers used as possible. And again, ironically, the smallest numbers is going to give you a much bigger piece than what you started with. Okay. All right. Anyway, you are looking to use fraction names for 1. Remember, the reason you're using fraction names for 1 is because whatever you do to the numerator, you must do to the denominator. All right, so today you're going to just work on, even though we were looking at and we were doing the lessons from 124 and 125, you only need to complete all of lesson 125, numbers 1 to 29. Number 1 to 29. Okay, and let's just do, we didn't do all of the practice ones, but we did most of them, and we did some additional ones. But let's just take a look here, and let's do 3/8 and 6/10. Okay, let's make these the last two that we work on together. All right, so 3/8. What fraction name are we going to divide 3/8 by? Okay, well, after going through 2/2, 3/3, 4/4, you should realize that 3 and 8, there's nothing that we can divide them both by, so 3/8 is already reduced. And 6/10. What can we divide 6 and 10 by? We can divide them both by 2, so we use 2/2, and 6 divided by 2 is 3, and 10 divided by 2 equals 5. Okay, so again, you just need to work on lesson 125, numbers 1 to 29, numbers 1 to 29, so in other words, all of lesson 25. Okay, and if you have any questions, please make sure you reach out to me so I can help you. Don't forget to put in some extra time on IXL and extra math, and I'll see you later. Bye.